Ever wondered how Google Maps finds the fastest route or how LinkedIn suggests your next connection? It all boils down to graphs. In this video, we will cover DSA graph algorithms, practice questions, and detailed explanations. Unlock the secrets of graph data structures with these 30 exam-style practice questions. In this video, we dive deep into 30 comprehensive practice questions covering the DSA graphs certification. We'll explore representations, traversals, shortest paths, and complex algorithms like Kruskals and Prims. Before we begin, make sure to grab a notebook. If you're looking for the full certification course, check the link in the description. Which data structure is most space efficient for representing a sparse graph with V vertices and E edges? Option A, adjacency matrix. Option B, adjacency list. Option C, incidence matrix. Option D, binary search tree. The correct answer is B. An adjacency matrix requires O(V) squared space regardless of the number of edges, which is wasteful for sparse graphs, where E is much smaller than V squared. An adjacency list only stores existing edges, resulting in a space complexity of O(V) plus E. This makes it significantly more efficient for networks like social media or roadmaps where each node is only connected to a few others. What is the time complexity of breadth first search, BFS, using an adjacency list representation? Option A, O(V). Option B, O(E). Option C, O(V plus E). Option D, O(V asterisk E). The correct answer is C. In BFS, every vertex is added to the queue exactly once, contributing O(V). For each vertex, we iterate over its adjacent edges. In an adjacency list, the sum of lengths of all adjacency lists is 2E for undirected graphs and E for directed graphs. Thus, the total time spent looking at edges is O(E). Combining these, the complexity is O(V plus E). If an adjacency matrix were used, the complexity would be O(V squared). Which algorithm is best suited for finding the shortest path from a single source in a graph that contains negative edge weights but no negative cycles? Option A, Dijkstra's algorithm. Option B, Bellman-Ford algorithm. Option C, Floyd-Warshall algorithm. Option D, Prim's algorithm. The correct answer is B. Dijkstra's algorithm fails with negative weights because it greedily assumes that once a node is visited, its shortest path is found. Bellman-Ford, however, relaxes all edges V1 times, allowing it to correctly calculate paths even when weights are negative. While Floyd-Warshall also handles negative weights, it is an all-pairs algorithm with O(V cubed) complexity, making Bellman-Ford O(V) more efficient for single-source problems. To detect a cycle in a directed graph, which of the following states during DFS indicates a cycle? Option A, encountering a node currently in the recursion stack. Option B, encountering a node already marked as visited. Option C, encountering a leaf node. Option D, reaching a node with no out degree. The correct answer is A. In a directed graph, a cycle exists if and only if a back edge is found during DFS. A back edge connects a vertex to one of its ancestors in the DFS tree. We track this using a recursion stack, or an array keeping track of nodes in the current path. If we encounter a node that is already in the recursion stack, it means we have looped back to an ancestor, confirming a cycle. Prim's algorithm for minimum spanning tree is based on which algorithmic paradigm? Option A, dynamic programming. Option B, divide and conquer. Option C, greedy. Option D, backtracking. The correct answer is C. Prim's algorithm follows the greedy paradigm. It starts with a single vertex, and at each step, it adds the cheapest edge that connects a vertex in the MST to a vertex outside the MST by making the local optimal choice at each step. It eventually achieves the global optimum, the minimum total weight for a spanning tree. What is the maximum number of edges in a simple undirected graph with n vertices? Option A, n, n1. Option B, n squared. Option C, n, n1, 2. Option D, 2n. The correct answer is C. In a simple undirected graph, each pair of vertices can have at most one edge. The number of ways to choose two vertices out of n is given by the combination formula $nc2 equals frac n. n1, $2. For a directed graph, the answer would be $n. n1, because each pair can have two directed edges, one in each direction. Topological sorting can be performed on which type of graph? Option A, any directed graph. Option B, undirected acyclic graph. Option C, directed acyclic graph. DAG. Option D, complete graph. The correct answer is C. Topological sorting is a linear ordering of vertices such that for every directed edge $u to versus vertex $u comes before $v. This is only possible if there are no cycles. If there is a cycle, no vertex in the cycle can come first. Therefore, it only applies to directed acyclic graphs. DAGs. What is the primary advantage of using the Floyd-Warshall algorithm over running Dijkstra's multiple times? Option A, it is faster for sparse graphs. Option B, it is simpler to implement using dynamic programming and handles negative weights. Option C, it has a lower time complexity than Dijkstra. Option D, it uses less memory. The correct answer is B. Floyd-Warshall is an all-pairs shortest path algorithm with a very simple triply nested loop structure. V cubed. Its main advantage is that it can handle negative edge weights, as long as there are no negative cycles, and is extremely easy to implement. While running Dijkstra v times with a Fibonacci heap is VE plus V squared log V. Floyd-Warshall remains the standard for dense graphs and general weight scenarios. Which data structure is typically used to efficiently implement Kruskal's algorithm? Option A, stack. Option B, queue. Option C, disjoint set union, DSU. Option D, hash table. The correct answer is C. Kruskal's algorithm works by sorting all edges and adding them one by one if they don't form a cycle. To check if adding an edge $u, v, forms a cycle, we need to know if $u and $v are already in the same connected component. The disjoint set union, DSU, with path compression and union by rank provides nearly constant time operations for find and union, making it the ideal choice for this task. In an adjacency matrix of an undirected graph, the matrix is always Option A, identity matrix. Option B, symmetric. Option C, asymmetric. Option D, upper triangular. The correct answer is B. In an undirected graph, if there is an edge between vertex $i$ and vertex $j$, then the entry at $a, I, j, $ is 1, or the weight, and the entry at $a, j, I, $ is also 1, because $a, I, j, equals a, j, I, $ for all $i, j $. The matrix is symmetric about the main diagonal. Which traversal is used to find the shortest path in an unweighted graph? Option A, DFS. Option B, BFS. Option C, preorder. Option D, postorder. The correct answer is B. BFS explores nodes level by level. In an unweighted graph, the first time a node is reached, it is guaranteed to be via the shortest path, minimum number of edges, from the source. DFS does not guarantee this, as it may go deep down one path and find a destination much later than a shorter path available at a shallower level. A graph where every vertex has the same degree is called a Option A, complete graph. Option B, regular graph. Option C, bipartite graph. Option D, connected graph. The correct answer is B. A regular graph is defined specifically by the property that all vertices have the same degree. For example, a three-regular graph is one where every node has exactly 3 edges. A complete graph is a specific type of regular graph where every node has degree $n-1. What is the time complexity of the Bellman-Ford algorithm? Option A, O, V plus E. Option B, O, V log V. Option C, O, V asterisk E. Option D, O, E log V. The correct answer is C. Bellman-Ford consists of an outer loop that runs $v minus $1 times. Inside this loop, it iterates over all $e$ edges to perform the relaxation step. This results in a total time complexity of $O, V1, asterisk E, $, which is simplified to $O, V asterisk E, $. What is a strongly connected component, SCC, in a directed graph? Option A, a subset of vertices where every vertex is reachable from every other vertex in that subset. Option B, a subset where every vertex has an edge to every other vertex. Option C, a component that remains connected after removing any one edge. Option D, a tree that spans all vertices. The correct answer is A. In a directed graph, an SCC is a maximal subgraph where for every pair of vertices $U, V, $, there is a path from $U$ to $V$ and a path from $V$ to $U$. Algorithms like Tarjan's or Kosaraju's are used to find these components in $O, V plus E, $time. A bipartite graph can be colored with how many colors such that no two adjacent vertices have the same color? Option A, 1. Option B, 2. Option C, 3. Option D, N. The correct answer is B. The definition of a bipartite graph is that its vertices can be divided into two disjoint sets such that every edge connects a vertex in one set to a vertex in the other. Therefore, you only need two colors, one for each set, to satisfy the coloring condition. If a graph contains an odd cycle, it is not bipartite. Dijkstra's algorithm is essentially a generalization of Option A, DFS, Option B, BFS, Option C, binary search, Option D, merge sort. The correct answer is B. BFS finds the shortest path in an unweighted graph by exploring neighbors level by level. Dijkstra's algorithm uses a priority queue instead of a standard queue to explore neighbors based on accumulated weight rather than just hop count, making it a generalization of BFS for weighted graphs. Which algorithm is used to find the transitive closure of a graph? Option A, Dijkstra's. Option B, Kahn's. Option C, Floyd-Warshall. Option D, Prim's. The correct answer is C. Transitive closure determines if there is a path between every pair of vertices $I, J, $. The Floyd-Warshall algorithm can be easily adapted for this by using Boolean OR instead of addition, and exists instead of distance, effectively filling the reachability matrix in $O, V cubed, $. What is the handshaking lemma in graph theory? Option A. The number of vertices with odd degree is always even. Option B. The sum of degrees is equal to the number of edges. Option C. Every graph has at least one cycle. Option D. A graph with n vertices has n1 edges. The correct answer is A. The handshaking lemma states that the sum of the degrees of all vertices in a graph is twice the number of edges. $2 e Since $2 e is always even, the sum of degrees must be even. This mathematically implies that there must be an even number of vertices with an odd degree. Using union find for cycle detection is most applicable to which type of graph? Option A. Directed graphs. Option B. Undirected graphs. Option C. Directed acyclic graphs. Option D. Bipartite graphs. The correct answer is B. Union find is excellent for detecting cycles in undirected graphs. As we process edges $U, V, $, we check if $U and $V belong to the same set. If they do, adding $U, V, completes a cycle. It is not directly applicable to directed graphs because the direction matters for cycle formation. A path must exist in a specific orientation. What is the time complexity of checking if an edge exists between two vertices in an adjacency matrix? Option A, O, 1. Option B, O, V. Option C, O, E. Option D, O, log V. The correct answer is A. In an adjacency matrix, we can directly access the element at matrix I, J, This is an array indexing operation, which takes constant time, $O, 1, $. In contrast, an adjacency list would require traversing the list of vertex $I, which takes $O, text degree of I, $. In Kruskal's algorithm, why do we sort the edges? Option A. To ensure we visit all vertices. Option B. To pick the smallest weight edge first. Greedy approach. Option C. To avoid using a disjoint set. Option D. To handle negative weights. The correct answer is B. Kruskal's is a greedy algorithm. By sorting edges from lowest to highest weight, we ensure that we always try to include the cheapest possible connections first, which is the core logic required to minimize the total weight of the spanning tree. An Euler path exists in an undirected connected graph if and only if. Option A. All vertices have even degree. Option B. Exactly 0 or 2 vertices have odd degree. Option C. The graph is a tree. Option D. The graph is a DAG. The correct answer is B. An Euler path is a trail that visits every edge exactly once. For this to be possible, the start and end nodes can have odd degrees. One edge to leave, enter. But all middle nodes must have even degrees to ensure every entry into the node has a corresponding exit. If 0 nodes are odd, it's an Euler circuit. If exactly 2 are odd, it's an Euler path. The Ford-Fulkerson algorithm is used to solve which problem? Option A. Shortest path. Option B. Minimum spanning tree. Option C. Maximum flow. Option D. Topological sort. The correct answer is C. The Ford-Fulkerson algorithm calculates the maximum flow in a flow network. It works by repeatedly finding, augmenting paths in a residual graph and increasing the flow until no more paths from source to sink exist. It is intrinsically linked to the max flow min-cut theorem. What is the time complexity of building an adjacency matrix for a graph with V vertices and E edges? Option A, O, V plus E. Option B, O, V squared. Option C, O, E. Option D, O, V squared plus E. The correct answer is B. To build an adjacency matrix, you must first initialize a $V IMS V matrix with zeros, which takes $O, V squared, $time. Then, you iterate through the $E edges to set the appropriate cells, which takes $O, E, $. Since $E is at most $V caret $2, the overall complexity is dominated by $O, V squared, $. Kahn's algorithm is used for Option A. Finding shortest paths. Option B. Topological sorting. Option C. Detecting articulation points. Option D. Finding SCCs. The correct answer is B. Kahn's algorithm is a popular BFS-based approach for topological sorting. It works by maintaining the in degree of all vertices, adding vertices within degree 0 to a queue, and iteratively removing them from the graph while updating the in degrees of their neighbors. An articulation point in a graph is a vertex that, when removed, Option A. Reduces the number of edges by half. Option B. Increases the number of connected components. Option C. Creates a cycle. Option D. Turns the graph into a tree. The correct answer is B. Articulation points, or cut vertices, are critical nodes in a network. Removing such a node disconnects the graph, or a component of it, thereby increasing the total number of connected components. These are often found using a modified DFS algorithm that tracks discovery and load times. A tree with n vertices has how many edges? Option A, n. Option B, n1. Option C, n plus 1. Option D, log n. The correct answer is B. By definition, a tree is a connected acyclic graph. One of the fundamental properties of a tree is that it always contains exactly n-1 edges. If it had more, there would be a cycle. If it had fewer, it would be disconnected. Which data structure is typically used for implementing depth-first search, DFS? Option A, queue. Option B, stack. Option C, priority queue. Option D, linked list. The correct answer is B. DFS explores a path as far as possible before backtracking. This last in, first out behavior is naturally handled by a stack. This can be either an explicit stack data structure or the implicit call stack provided by recursion. In Dijkstra's algorithm, what happens if we use a Fibonacci heap instead of a binary heap for the priority queue? Option A. The time complexity remains $O, E log V, $. Option B. The time complexity improves to $O, E plus V log V, $. Option C. The time complexity becomes $O, V squared, $. Option D. The algorithm fails to find the shortest path. The correct answer is B. A Fibonacci heap has a better amortized time complexity for the decrease key operation. $O, $1, compared to $O, log V, $, for binary heaps. Since Dijkstra's performs $V extract mn and up to $E decrease key operations, the complexity drops from $O, V plus E, log V, $, to $O, E plus V log V, $, which is a significant improvement for dense graphs. Which of these is not a real-world application of graph algorithms? Option A. GPS navigation. Option B. Social media recommendations. Option C. Sorting a list of numbers. Option D. Compiler dependency resolution. The correct answer is C. Sorting a list of numbers is a linear data structure problem typically solved with comparison or distribution-based algorithms like quicksort or mergeasort. GPS, shortest path, social media, connectivity, clustering, and compilers, topological sort for dependencies, are all classic applications of graph theory. That concludes our 30-question deep dive into graphs. If you found these explanations helpful, you're well on your way to mastering DSA. Don't forget to like this video and subscribe for more algorithm practice. Your support helps us create more free educational content. For the complete set of 500+ questions and a deep dive syllabus, use the Udemy link provided below.